Thanks for having me here. Excited to be here, the first time I'm at this. So obviously some interesting conversation earlier today on the climate piece and reframing that, and a good stage set. It's been 2 years, I think, since I last chatted with Steve, so I appreciate the kind of setting the groundwork for nuclear being a big, important part of the future on this. So at Oklo, we're working on next generation nuclear reactors to kind of play into this massive opportunity here. By way of background and context, I'm born and raised in New Mexico, so a four-corner state here. Grew up around nuclear, had a fun, kind of weird experience of getting hired into the nuclear weapons program when I was 16. I know that was it. I got a Q clearance, which is a top secret clearance, only about 3 months after I got a driver's license. Weird, but cool set of experiences to get exposed to this technology that I had fallen in love with when I was a kid and knew I wanted to work on. From that, I got to springboard into a bunch of different facets of the industry and realized that, like, for all of sort of the fundamental physics reasons that make nuclear wonderful from a technological perspective, it's going to make it ultimately inevitable as kind of the main power source looking forward. So I set out with my co-founder to start the company back in 2013 to kind of play into this and do things a little bit differently. We long envisioned that there'd be a clear recognition of, like, look, we always have needed more power. We're pretty confident that trend was not going to change, even though there were some prevailing thoughts that were not the case back in maybe 2013, 14, thinking about efficiency and other things like that would change that paradigm. Never made sense to us because you'd have a panel talking about that, and then right after would be somebody talking about, we're going to need 3x the power to drive electrification of transit and everything else. So it was pretty clear that we're going to need a lot more power. And the way, like, industrialized societies have worked is they do really well when they need power, when they have that sort of as a 24/7 reliable source of power that's also affordable. And nuclear really plays well into that. We also started the company about right before we formally incorporated. We met a guy named Sam Altman, who was actually looking at starting a nuclear company because he saw nuclear was so important and energy was kind of the key to abundance going forward. And he will say now, today, clearly, that abundant intelligence is ultimately going to be built on abundant energy. And so while AI wasn't exactly in the crosshairs then, it was a clear trajectory of what it might enable. Fast forward a few years, obviously, the world changed radically. And in the last few years, that confluence of us kind of saying, hey, we're going to need more energy, driving things like electrification, driving reindustrialization in the US, but then this massive change with what's happened with compute and AI is kind of making basically setting the stage for nuclear to be massively inevitable. That's a silly way of saying, like, the compute energy needs to drive the future that we're seeing happen now are largely going to drive forward and make kind of the deployment of new nuclear power inevitable, which is awesome. And growth at a rate that I think historically people have been probably hesitant to fully understand. So I'm going to talk to you a little bit today about why nuclear fission specifically is really well positioned for this, what we're doing in it, and why some of the paradigms that we think about that make nuclear hard to build, expensive, take a long time, all that kind of stuff, aren't actually exactly true from a physics perspective, and why there's room for innovation to completely change that paradigm. I don't have to spend a lot of time on this slide. I think a lot of folks see similar numbers, similar plots. It's big numbers coming forward. And I think at the end of the day, we've also combined this with a world where we, especially in the United States, have been resting on the benefits, quote unquote, of shipping jobs and baseload energy demand offshore, and then replacing it with renewable intermittency that has not exactly kept up, and now we have a pretty significant energy crunch. It's a good time to be in this business, but we are behind in being able to provide power to this. So taking new approaches are going to be key to sort of unlocking doing things in a reasonable time frame. So, real quick thing I like the context set into. I want to break down all the paradigms people have, right? Because I'm sure folks have said this, like, hey, or have thought of this and heard this and see this in the press. Nuclear's too expensive. It takes too long to build, all these things. Those don't have to be true. And the best way to articulate this is the material efficiency it has. I think the truest sort of metric of economic potential and also deployment potential is the raw material footprint per megawatt hour of energy produced across all energy sources. To underscore this, fission starts with a great fuel. When you go into the strong nuclear force, one of the 4 fundamental forces that we know about in the universe that holds the nucleus together, and you release it or unleash it, you tap into something that's many orders of magnitude greater than everything we've lived in today around that, in the electron shell. That's kind of a nerdy way of saying when you split an atom, you get millions of times more energy than when you do combustion or oxidation reactions. And to put that in context, a golf ball of uranium metal would have all the energy content you need to power your entire lifetime's energy needs, right? So it's a massively scalable resource. But then out from that, nuclear fission actually makes really usable power because the primary realization of splitting atoms is heat. And that's heat that's actually manageably controllable and harnessable and harvestable and turned into something we can do things with. And that translates to this, which is the life cycle material use that I just talked about. To read this chart, this is a bar chart that just shows the number of kilograms of materials needed. So copper, concrete, steel, fuel, things like that, needed per gigawatt hour of energy produced. And as you can see, nuclear fission requires by far the least. In fact, you really have to zoom in to see that advantage. That means it uses the fewest materials, radically so, than everything else that we build quickly and efficiently. Why can't you do that with nuclear? Well, you can. You just kind of have to think about how you actually tackle this problem in a modern lens. Because what's happened in nuclear was a massive amount of stagnation for a couple decades, for a lot of factors, and we don't have time to get into all of that. It's a confluence of things like public perception, like, anti-nuclearism from the weapons side. I do think, yes, the accidents that happened in the past fed that, but also an industry that was not innovating and dynamically adapting to where the market was growing. Ever bigger plants made it ever harder to build for smaller utilities, where the ecosystem of sort of that market was back in the 70s. It wasn't supportive of that, not supportive today. We didn't modernize how we approach things technologically or from a business model and go-to-market perspective. Well, now we have this new wave of innovation, like what we're doing, to change that. So we rethought some of these things fundamentally. One is on the business model. We don't actually ask people to buy the power plants. In fact, that's not even what the industry did. They would design the power plants to like 50% completion and then ask utilities to pay you a couple $100 million to take the blueprints, not even fully complete, and then design, build, do it all yourself. Very frictional. We actually design, build, operate the plants ourselves, sell the power. That's what people want. We see that that's where the market's been moving, with the hyperscalers signing PPAs because they want the power, they don't want the power plants. So great to see that as a key angle to sort of change what's made nuclear hard in the past. There's other dynamics to that too that I'll talk about in a second. But the other factors we looked at is taking advantage of the inherent kind of efficiency nuclear has from a materials perspective that lends itself to being, I guess, better able to take advantage of those capabilities and strategic advantages it has by taking newer technologies, but actually demonstrated that are very material efficient, that can leverage existing supply chains and going smaller. So to the business model side, it's really complex to build a nuclear power plant, or it's not. It can be, but it doesn't have to be. And the typical play is everything on the top of this chart. Lots of stakeholders, lots of interaction points and interface points that are difficult. We don't do that. We just do it all in-house. Yes, we subcontract those things out, but we own it all full stack, so it's an easy delivery model of what needs to happen here. That changes the paradigm radically and gives you more control. The other thing we do is take advantage of wonderful technology research and development that's been ongoing, frankly, since the tail end of the Manhattan Project, but wasn't commercially ready really until, I would say, the 80s and 90s. And this is manifest by technological improvements and innovations, specifically using advanced coolants and different types of reactors. In our case, a liquid metal-cooled fast reactor. To avoid a bunch of technical jargon, what this is it uses liquid sodium as a metallic coolant, really good at operating at high temperatures without being pressurized, compatible with common stainless alloys that many other industries use, has a wonderful history of operation behind it, can realize these incredible sort of inherent and passive safety features. In other words, basically systems that are self-stabilizing and self-cooling, so they're walk-away safe, and they can recycle fuel. In other words, they take waste and keep using it and using it and using it and burning it down. And that unlocks a huge amount more energy potential in the system. And we know this works. This isn't paper, it's been done. It's about almost 500 combined reactor years of operational experience have been accumulated around the world. Notably in the US, we demonstrated this with two very successful, I would say, near commercial demonstrations. This is the one we highlight. It was called the Experimental Breeder Reactor 2. Produced about 20 megawatts of electric power for 30 years. Actually outperformed today's power plants in the main sort of operating characteristics that matter. Demonstrated the safety characteristics and demonstrated the fact that it could run on waste. In fact, this happened only a few hundred miles from here up in Idaho Falls. So all of that translates then to the ability to sort of tap into the broad potential this technology has. So when I talk about how do you realize that sort of material advantage, one of the ways you do it is by designing a system that's inherently and passively safe. So you're not relying on active systems to keep the reactor running, to keep it safe, because those things cost a lot of money. And those are the big cost drivers typically in nuclear. And what the nuclear industry refers to them as is safety related or nuclear rated or nuclear grade. What that translates to is having a lot more regulatory oversight that go on from everything from design through procurement through installation and operations. And those things will cost 10 to 50 to 1,000 times more than the same commercial sort of grade components that you could otherwise get. If you're familiar with the sort of phraseology of an idiot index, which is the multiplier on the cost of raw materials in to the cost of the finished product, nuclear safety-related systems have some of the highest idiot indexes that there are. So one way to reduce costs and complexity in nuclear is just don't have them, because you're relying on gravity, you're relying on thermal convection, you're relying on thermal conduction, things that are naturally given to us. So this system does that. That's a big one. Another thing is start small. Smaller systems have less fuel, less radioactive materials, less stuff to have to manage. It actually lends itself to having fewer safety-related systems. That's a big change and a big paradigm shift. And then the other factor here is you modernize how you actually do the things that, like, you deliver the components that actually are safety-related. And the way you do that is just by modernizing the industrial approach. I said earlier the industry stagnated. It did. It stagnated for decades. The industrial quality assurance mechanisms used in nuclear look pretty much like they did in the 1970s. Pen and paper. Imagine building a $40 billion project with pen and paper quality assurance for lots of major parts on it. Well, we did that. It wasn't a good idea, but we did it, and we learned, like, there are better ways to do this. It wasn't all paper. There was digital stuff too, but you can modernize how this is done thanks to advances in other industries, like what, just generically speaking, ISO 9000 allows you to do. Those same things meet the same quality requirements, and there are ways you can do that. Well, we've kind of shown and gotten regulatory actually, we weren't even the first. The industry's been doing this for a while, just combining this whole approach, fewer parts that are safety related, more modern ways of doing it, massive unlock in terms of what you can do in terms of cost and scale and speed to build. So how this works, what it looks like, you have a reactor where you have fuel that are in pins, like rods literally, that are about the diameter of about my index finger, about 8 feet tall. You have a couple thousand of them in a hexagonal pattern. They're basically immersed in this reactor module, which is filled with a pool of liquid sodium. They produce heat. It's transferred to that liquid sodium, which then ultimately transfers heat to boil water, which makes steam, which spins a turbine, makes electricity. The excess heat that you can't make into electricity, you reject to the air, and then off you go. And that's a great way to sort of realize that in a system like this, it's remarkably simple compared to how we've done nuclear in the past, afforded by the things I talked about. What that translates to is the benefits of having a lot fewer parts that come from the conventional nuclear supply chains that are slow and inefficient and expensive. So this is kind of the key ways in which you start to unlock the true potential that nuclear has from an economic superiority perspective. So then the question turns into, well, okay, you're talking about small plants, but we're talking about gigawatts upon gigawatts of new capacity. How do you do this? Well, a feature of being small is you can prefabricate, but more importantly, you can actually organically build up with how customers are actually scaling and deploying power at the data center side. Yes, there's a rush because we're behind on compute, so you're seeing a lot more go. But when you talk to customers about their planning, unfortunately, we really just can't bring new nuclear power online before 2027, and that's really aggressive as well. But when you talk about that time frame and beyond, you get into a world where you are building out in a synced fashion that matches what they're going to be growing into, one for one, rather than building a big plant that you have to fill up as they grow into it. That presents a lot of stranded asset risk if you build a gigawatt plant and you only have firm 200 megawatts of offtake, but you're pretty confident you'll get to that gigawatt, but you don't have it in firm offtake. We start at 75 megawatts, and that matches really, really well with the data halls as we see being built out at the data center level, and then we can grow with them organically. It also allows us to have a much better profile, forgive the little graphic typo, but to match the fact that pretty much all power plants are going to have to come offline for some maintenance of some sort. This allows us to stagger that and phase it so you're delivering the quality of power that they need, which by the time you sort of plan for this, you can either reduce the amount of backup you need or just overbuild and have backup capacity that allows you to deliver that multiple nines of reliability and availability they need to have. And you can build these things completely independently and grow out organically from this. And we found a lot of traction with this. So we've announced about 14 gigawatts of basically order interest, which is great. We've not signed any binding offtake agreements because we've watched in that time the price of power go up by 2x, so we don't want to lock ourselves into anything too fast, but also find the right ways to partner with folks on this. So it's a pretty exciting time in the space, and I think this is barely the tip of the iceberg, candidly. And of course, this is going to keep us really busy, but this tells you people like this kind of model and believe that you can do nuclear in a different way. So one of the other questions that comes up is, what about licensing and regulatory? And it's really, really hard. And yes, it is challenging. And yes, we've definitely been through the mud on it. But we've leaned into that because, like I said earlier, the ways you reduce costs or take advantage of inherent passively safe and simple designs that are smaller to reduce the regulatory burden. So we've made a lot of headway with that. Historically, the industry assumed you had to do things like those top two bars. This multi-step, multi-process, things that take many years, right? Like 6 to 10 years, but you don't have to. We saw an opportunity 6 years ago to lean into this on the heels of some legislation that passed that shortened the timeline or capped it at 36 months. A year ago, they passed the bill, signed into law, capped it at 25 months. And then just 2 months ago, in a few days, the president signed an executive order that capped it at 18 months. And you've seen the NRC move all this stuff forward. So we're actually finding that the permitting parts of nuclear are weirdly enough and counterintuitively enough a strategic advantage for the technology because it allows you to move more quickly in permitting in certain cases because it's all encompassing of safety, but also siting and environmental. There's work to do here. This is not a slam dunk. It's going to be challenging because this is a total organizational shift in terms of how, not total, but a significant organizational shift in terms of how the nuclear regulator is operated. But the cool thing is we're revisiting sort of the Atoms for Peace era of the 50s where we're opening up the aperture to use other pathways for regulatory authorization that do exist in this country, like the Department of Energy and like the Department of Defense that actually have a clear need set and can move things along at a slightly different way, but a way that the NRC can adapt from. But they're really good at taking something done and optimizing it and doing really well. And so we're finding, I'm giving them some credit on that, but we're finding that there's a really interesting environment culminating right now that is clearly building on the tailwinds that I just talked about and ultimately going to make nuclear quite inevitable in this sense. So we like where we're positioned, kind of doing things in a quite different way and ultimately allowing us to tap into some of these inherent benefits that nuclear has. But one of the main things I really wanted to hit on today was the fact that we can do nuclear differently. It doesn't have to be huge, it doesn't have to be massively expensive, and it doesn't have to take forever to do. We can tap into existing supply chains that existing industries like oil and gas, food and beverage, chemical use to make the same parts you need in nuclear plants at massive volumes and scales, domestically, mind you. You can do things in a way that say, hey, these plants are relying on natural phenomena, like in this reactor, when it heats up, the fuel thermally expands and shuts itself down naturally. It's able to cool itself off just by the natural circulation of the sodium and the natural circulation of air outside, thanks to properties like buoyancy and thermal conduction and thermal convection and thermal radiation. All of those factors kind of combine to allow you to have a system that then has fewer things you need to bolt onto it to keep it operating safe that cost a lot of money, which make it a lot faster to scale because you need fewer things, but also quite a bit cheaper. And you can tap into what these technologies unlocked with respect to fuel efficiency. I hinted at it, but just to wrap up here before we get into questions, one of the things fast reactors, and that's what we're doing, can do, is recycle fuel. Why that matters is today, reactors can only, well, not even, just in general, almost any nuclear reactor is going to use only about 5, maybe 10% of the fuel that's loaded into it in a single pass. You could go more, technically, for sure, but that comes at the cost of needing a lot more systems to manage and contain that extra fuel. Or control, really, that extra fuel. So it's typically the optimum is about 5% or so. That means that 90 to 95% of the waste that comes out of today's plants is actually just unused fuel that can be recovered and reused. And it's through recycling technology. In fact, a small scale of it is happening today as we speak, a few hundred miles from here in Idaho Falls to produce fuel for our first plant. But that technology can allow you to then tap into that massive reserve. To put a number on it, there's a little over 90,000 metric tons of used fuel in the United States. That number might sound like a lot or not, depending on your context, but it's not that much volume. But there's enough energy content in that from recycling to power the entire country's energy needs for over 150 years. It's 1.2 trillion barrels of oil equivalent of energy that's just sitting there stranded that we think of as a waste. Then you go further. When you enrich uranium, you have to actually take the one isotope that naturally occurs at 0.7%, uranium-235, and concentrate it. In so doing, you have to leave behind uranium-238, the other natural occurring isotope of uranium. There's about 700,000 plus metric tons of that. So you kind of do the math, or more than that. So you do all the math, there's about 12 trillion barrels of oil equivalent sitting in what we consider waste inventories and stockpiles today. It's enough energy to power the entire country's power needs for a millennia. Oh, and by the way, every year our operating plants produce enough waste to power the country for 4 more years. So at scale, those are big numbers, but this means you can take this technology, tap into known reserves of heavy metals like uranium, thorium on this planet that we know how to access, and power the entire planet's energy needs for 5+ billion years. So either by then the sun will consume the planet, we'll figure out how to move the planet, or we'll keep the sun running. I don't know. We'll figure something out. I feel pretty good about the energy future because this is technology we know works and we know we can figure out different ways to scale and deploy it. And nuclear fission has been shy about this message for no good reason. But the fact is we can do this, and the science is behind it. The physics have been shown to work, and the early stage engineering has already been done. Now it's a matter of modernizing it and scaling it forward. So I do feel really good about the future on that front, and that is definitely what we're working to deliver into.